In this video, we study a very basic problem in distributed systems. How can we broadcast data in a fault-tolerant way? Let's start simple. Given a distributed system consisting of nodes that can all interact directly by exchanging messages over some communication channel, there is a node, called the sender, that has some data to share with all other nodes. In the example here, the sender wants to broadcast the number 8, that is, it wants to send this number to all other nodes. How can this be achieved? Since each node has a communication channel to all other nodes, it can simply send a message containing the number 8 to each other node. When they receive this message, they can all store it and the broadcast is complete. We call this simple protocol a best effort broadcast. This is easy enough, but what happens if things go wrong? Let's say the sender manages to send off the first message and then it crashes. The recipient of the message can still store it, but is it still a broadcast if only a single node receives it? The recipient doesn't know whether the message will also be received by other nodes. In the example here, this is not the case. The other nodes may never receive this value. What about arbitrary failures or even malicious behavior? If a node can exhibit any kind of faulty behavior, we call it a Byzantine node. If the sender is Byzantine, it could even send every node a different message. As a result, every node has a different understanding of what the broadcast value is. Also in this scenario, we didn't really achieve that all correct nodes agree on the broadcast message. How can we address this? First, we need to define our goal more concretely. As we said before, a correct node would like some assurance that other nodes will also see the message that it received. This property is usually called totality. If a broadcast routine has the totality property, it means that if a correct node delivers a certain message, it may take some time, but eventually, all correct nodes will deliver this message. Here, deliver means that the node accepts this message as the result of the broadcast. Totality alone is actually quite simple to guarantee. Let's look at a simple round-based algorithm. In the first round, the sender broadcasts the message as before. But then, in the second round, if a node receives the message from the sender for the first time, it also broadcasts the message and then delivers it. We will now show that this simple algorithm achieves totality. It actually guarantees that validity holds as well. We say that an algorithm has the validity property if the message sent by a correct node is delivered at all correct nodes. Let's start with totality. If there is a correct node V that delivers the message, it must have broadcast the same message before delivering. But since it broadcast the message before delivering, this means that all other nodes will eventually receive it, broadcast it and deliver it. It is easy to see that the algorithm also has the validity property. If a correct node broadcasts a value, all other correct nodes will receive it, broadcast it and finally deliver it. This simple algorithm even works for any number of failures. While the algorithm is simple, it has a shortcoming. It doesn't prevent any node from broadcasting an unbounded number of messages, which would cause a huge load on the distributed system because every node sends everything to all other nodes. It would be great if every node could only broadcast one message once in a while, for example, once every execution round of some other algorithm that depends on messages being broadcast. We will now look at an algorithm that achieves exactly that. In the first round, the sender again broadcasts the message, but this time it also indicates the round number R for this broadcast. Recall that any node can only broadcast one value per round. When a node receives such a value round number pair and it is the first such message from the sender for this round, it broadcasts an echo message containing again the value plus the round number. Note that it also broadcasts an echo message if it receives n-2f such echo messages, where f denotes the maximum number of faulty nodes that the algorithm can handle. We will specify the value of f later. Nodes collect these echo messages until they receive at least n-f of these messages. Once they have n-f echo messages and the message for the previous round has been delivered, the node delivers the message for round R. We will now show that the algorithm not only has the totality and validity properties, but also an agreement property, which states that the nodes agree on the value that a node has broadcast for any round. In other words, there can be at most one delivered broadcast message per node and round. If there are only crash failures, that is, a faulty node completely crashes and does not execute any more steps or send any more messages until the end of the execution, the algorithm works as long as the majority is correct. We will further show that the algorithm can tolerate any kind of failure as long as less than 1/5 of all nodes exhibit Byzantine behavior. Let's start with totality. Assume that some node V delivers message XR. We know that node VA must have received n-f echo messages. This means that all correct nodes will eventually receive at least n-2f echo messages because at most f nodes are faulty. Since every correct node broadcasts the echo message when it receives n-2f echo messages, it follows that all correct nodes will eventually broadcast the echo message. Since there are at most f failures, every correct node will receive at least n-f echo messages and then deliver the message. It is easy to show that validity holds too. The correct sender broadcasts the message, which causes every correct node to broadcast an echo message. As a result, all correct nodes will receive n-f echo messages and deliver the message. Let's now show that there is also agreement among the nodes, that is, correct nodes deliver the same value. First, we focus on the case of crash failures. This is easy to see because the nodes all execute the algorithm correctly until they crash, so no node will ever send conflicting messages for the same round. The Byzantine failure case is a bit trickier. A correct node may send an echo message for a value x if it receives n-2f echo messages. At least n-3f echo messages must be from correct nodes that received the message from the sender. The same is true for any other value x prime. Since a correct node only accepts one message for a particular sender and round, we get that there must be at least 2 times n-3f correct nodes, but if f is less than 1/5 of n, there must be more than n-f correct nodes, which is a contradiction because there might be f faulty nodes. In conclusion, we looked at the broadcast problem, focusing on the problem of dealing with failure, which could be either crash failures or arbitrary, so-called Byzantine failures. We learned that it is quite simple to ensure that all nodes see all delivered messages, but this may cause a storm of messages. We then also looked at a slightly more complex algorithm that further guarantees that every node can only broadcast one message per round. It is worth pointing out that this is merely an introduction into the broadcast topic. There are many more interesting broadcast algorithms with various useful properties. Thanks for watching.